recording, and then I have to figure out how to share this with you guys. Give me a second. Let's see. Can you guys see the PowerPoint?
Oh.
All right, hold on. Can you see it now?
Yeah, we can see it.
Okay. All right. So PLC field devices. The main one is a relay. We've talked about relays before, but just be aware there's two types of relays that are important for PLCs. The first type is the logic relay, and these are what we represented in class as switches. You know, if you have switches in series, that represents AND logic. If you have switches in parallel, that represents OR logic. If you have a normally closed push button, we can use that as a NOT. We'll actually, instead of physical switches that a human would have to interact with, of course, you know these are done by used to be done by relay contacts. They'd have several relay contacts in series to represent AND or parallel to represent OR. So those kind of relays are small, low power relays that's used to make logic decisions. That's not what this PowerPoint is about. This PowerPoint is about what if you want to take something like an elevator motor or some heavy duty machine and connect it to a PLC whose current output might be a few milliamps, or voltage output might be a few volts. How would you connect a heavy machine to a PLC? And to do that, one way to do it is to use a control relay. So think of a control relay as an interface, a way to interface a low power circuit and a high power circuit together. And we've looked at relays before, but here's a diagram of a relay. You can see a couple things that hopefully you recognize. A relay is an electromagnetic device. There's a coil, and this coil, when you apply current to it, becomes an electromagnet. It energizes, and this part called the armature, when that coil is energized and magnetizes, that armature is pulled down. There's a spring over here on the side you can see that provides a force to either keep the contact open, keep the armature up or down. So if you think about on the end of this armature, there's a connection point right here. There's a connection point. And then here is a contact. Now this right now, the way you see it in the PowerPoint, this relay has no power on it. So it's in its normal state, its normal condition. And so notice there's two contacts here. There's one here at the top and there's one at the bottom. If this relay, if I laid it on the table, no power applied to it, it's in its normal state. The top contact, we say, is normally closed. The spring is keeping that contact closed, which means the bottom contact is normally open. And of course, if I apply power to it, the magnet will pull the armature down, and the armature will now contact the lower contact, which is the normally open contact. So here, I have choices. I can connect to the normally closed contact. I can connect to the normally open contact. It depends on what I'm doing. But the three main things, the three main parts to be aware of, the coil, which provides power, actually controls the relay, the armature. the normally closed contact, and the normally open contact. Of course, you've seen it like this. This is the actual symbol we use to represent the coil. In our PLC talk, we use a circle with some kind of name or address. So that represents the coil. And then you had the normally open and the normally closed contact. Of course, that represents the normally closed and the normally open contact. So you're looking at it, you're used to looking at it from a schematic point of view, which is nice to see the physical device, but here's how we're used to thinking about it. So we have a control relay coil, we have the normally closed contact, and we have the normally open contact. And we can use this relay because the coil circuit, that coil circuit is a low current circuit. At most, it's going to pull milliamps. It can pull milliamps of current. Well, that armature circuit, the one at the top, the one that moves, that can handle amps. It can handle tens of amps. It can even handle hundreds and thousands of amps depending on the size of the relay. So basically, I can connect the coil circuit to the PLC directly, a low current circuit, and have it switch a high current or high voltage circuit, and the two are really physically and electrically separated from each other. The armature contact section of the relay is totally isolated from the coil. So again, the coil is a low current circuit, the armature and these contacts are high current, so I can use a small current to control a large current. I use for an example for this your car starter. When you stick your key in the ignition and turn your starter motor over, that starter motor is probably pulling about 10, 15 amps. That's a lot of current. 1 amp is a huge amount of current. And so when you put your key in the ignition switch itself cannot or will not, is not designed to handle 10 amps of current. That's a lot of current. The part you control with your key switch would be the coil circuit. You stick your key in, you turn a low current switch, and so you're controlling current to basically a coil that electromagnetically moves the armature down to actually engage the starter motor. So there's an example where you're using a low current circuit, i.e. your ignition circuit or switch, to control a large circuit or current, your starter motor in your car. That's a good example. So you've seen these symbols before in your relay ladder logic. Now here's something new though. There's a relay, and we start with that, a basic relay, and then we build up from that. There's two other devices. This next one is called a contactor. A contactor. Think of a contactor as just a heavy duty relay. It's a super huge relay. Notice in the picture though, there's 3 contacts, or as I say, 3 poles here. There's a coil, and there's 3 sets of contacts here. And the contacts have L1, L2, L3 for line 1, line 2, and 3. And then it has these T connectors that actually connect up to a device. Now, why are there 3 contacts? Well, the reason there's 3 contacts is, first let me say that this particular contactor is not designed to switch DC. Relays can switch, as you know, relays can switch either AC or DC. Here we're referring to AC relays. And this contactor has 3 contacts or 3 poles because when we talk about AC, we can talk about something called phase. Now you may or may not be familiar with phase, but basically some of you already know that AC stands for alternating current. So it's with DC, you have a voltage that's steady, the polarity is constant, and you have a current that moves in one direction and whose magnitude is constant. And AC is quite the opposite. In AC, the voltage polarity changes at a regular time or interval or period, and the current direction changes. It alternates back and forth. The current alternates back and forth, and the voltage polarity alternates back and forth. The reason for that is because it's efficient, it's way more efficient to transmit energy over a large distance in the form of AC than it is if we did it with DC. It used to be done a long time ago, like the late 1800s. Energy, we move power around in the form of DC. We have Edison to thank for that. But that was a very, very inefficient system that Edison had. And so this guy, you may have heard of Nikola Tesla, came up with a better way to transmit power. And they call him the father of AC because of a device called a transformer. We're able to step AC voltages up real high, which lowers the current. And by sending AC power out at a high voltage, low current, turns out it's much, much more efficient to transmit energy that way. So that's why we have AC and DC. We have AC to transmit the power for the most part. And when we get the power where we need it, often we change that AC to DC. So you might plug your cell phone or your computer into the wall, thinking that you're plugging it in the AC, which you are, but that device has circuitry in it to change the AC from the wall back into DC. Now back to these three poles, these three contacts. When we talk about AC, alternating current, you can have a single sine wave of AC voltage or current that you transmit, but typically we transmit what we call three-phase power. You may have heard of three-phase. If you have a washer or heavy equipment in your basement that you plug in a big special plug that plugs into your, maybe for a dryer, you see it often with the dryer. They have a 240 volt. You know, AC in the house is usually 120, but you can have a machine like a dryer that's 240 will be 242 phase. 242 phase. Well, it turns out that you can have a single phase AC voltage or current, which is when you plug something into a wall outlet, that's mainly what you have. Single phase 120 volts, one sine wave. You can have a two phase 240 volts, or in this case, I'm showing you this contactor with three contacts. Because when they actually transmit AC power from the generator, when you're driving down the highway and you see those big, huge electrical towers strung over, say like a cornfield or something, that's three-phase power. And so AC is way more efficient than DC to transmit. Three-phase AC is even more efficient to transmit. So one reason for efficiency, we have three-phase AC. And the other reason we have three-phase AC is that some AC motors, large motors, it's easy to start those with three-phase, easier to start with three-phase than single-phase. So I said all that to say, don't let these three contacts here fool you. It's just three-phase power, which you really don't have to know about to understand the device. I just want to point out to you that we are talking three-phase now. But it's the same situation as the relay. You have basically a coil, and you have contacts, and these contacts shown here are normally open, but there's no reason why we can't have normally closed contacts. The point is, this contactor is a heavy-duty relay. That's the reason. That's the way I want you to think about it: a heavy-duty relay, and it's designed to handle three-phase power. Probably most big industrial machines that are electrical are three-phase, and so they would use this this contactor. So you have the relay, which is the basic unit. You have the contactor, which is basically a heavy-duty three-phase relay. And then there's one more called a motor starter. A motor starter is just what the name says. We use it to start motors. And so think of a motor starter as a contactor. And I told you to think of a contactor as a heavy-duty relay. Think of a motor starter as a contactor with built-in protection circuits. Built-in protection circuits. So if I show you the diagram, that you don't really have to memorize this diagram. This is the electrical diagram for a motor starter, the wiring diagram. But on the next slide, I'll show you a symbol of the actual device. It's a lot easier to understand. Some of this you recognize already, though. You have a three-phase motor. This is the device I'm connecting to these connectors, T1, T2, and T3. You recognize that. Basically, this is a contactor. There are your three normally open contacts. Here is your main control relay coil. Now remember, the address M corresponds to these contacts right here. So I have three-phase contactor with the coil. And in addition to that, I have overload circuitry in each phase here that you see. So basically, a motor starter is a contactor with protection circuitry. The other thing that you'll recognize the top part of this is a low current circuit. That low current circuit I can connect directly to the PLC. And on the bottom I have a high current circuit. Like I said with the relay, we use a low current circuit, i.e. the coil for a relay, to control a high current circuit, that is whatever you're switching. Well, here with this motor starter, I can connect the low current circuit directly to the PLC, and then that low current circuit would switch or control the three-phase motor. And that three-phase motor can be a huge motor like an elevator motor or some really big industrial machine. The other thing you'll recognize, hopefully, is this circuit here. This is a common standard circuit. That's your fill-in circuit that we talk so much about in class. Your fill-in circuit or latch, and then your reset or your stop button. So that you're already familiar with. So 3 levels of relays you want to know about. First is the basic relay. From that, we have a contactor, which is just a heavy-duty relay, usually 3-phase. And if I add protection circuit to it, then we have a motor starter. And this next picture here is a little easier to see because it's the actual physical device. Here I have the PLC. I have this start-stop button right here, the start-stop button. I have the start-stop button here into the PLC as an input. And notice there's one line. This output is a low current, low voltage line. And it goes to that motor starter. So I might have milliamps controlling tens, hundreds, or even thousands of amps in this motor starter. And there's my T lines, the device I'm controlling, the 3-phase motor. And these are the incoming 3-phase power lines. So again, relay, basic relay, contactor, heavy duty relay, 3-phase, and then the motor starter is a contactor with control circuitry. So I'll probably ask you guys about that on the exam, but since it's a take-home exam and you have access to all the material on Blackboard, I'm sure that won't be an issue for anybody. So those are our relays. And now we have, just kind of quickly, there's many types of sensors and switches that we could connect as input or output devices to a PLC. And again, I have some documents. One is on Blackboard. I think the one on sensors and transducers is already on Blackboard. But there's another one that I have to put up there on output devices. I got that on my Google Drive. I'll switch it over and I'll send you an announcement when I get that out. You'll need that for your exam. But here are some typical switches to be familiar with if you ever have to work with this. Everybody knows what a push button is, like a doorbell. There's toggle switches. You can switch. You can move the contact one way and it stays there. You can move it back the other way and it stays there. There's usually some kind of lever that you can move back and forth, a rocker arm, a lever, or something of that sort. There's a knife switch. Those are the ones that you might see in the old Frankenstein movies where you take it and you throw it over and it actually goes between these two metal contacts. The part that you move looks like a knife, and it goes between these two metal contacts. Selector switches. If you remember, well, you guys probably don't remember, but back in the day before they had remote control devices like TVs, I know it's hard to believe, but you had to actually get up and walk across the room to change the channel. And that click, the switch that you can change the different positions is what we call a selector switch. And then the dip switch, DIP, dual inline package switch. You've probably seen that before. If you have a garage door opener or maybe a car alarm switch, sometimes you have a garage door opener or a car alarm where you can take it apart. You can open up maybe a door and there's a set of little white switches that you can click either one way or the other, usually to set some kind of a code. That's what we mean by dip switches. What I would say to you is at some point when you go to review the material, just go to Google or YouTube and just YouTube some of these, just so you can Google some of these so you can see kind of what these look like. You don't need it for what we're going to do in class, but you never know when you guys start working, co-oping, you get out there, you might come face to face with the PLC, and you probably won't have to program it directly, but it is good to know what some of these devices look like in case you do have to put your hands on it or interact with it some kind of way. So I would recommend Googling these and just kind of getting a visual of what they look like. Some of these you're familiar with. Normally open push button, normally close push button. We talked about the one at the bottom is a make break push button.
Hey, Ron.
Yes.
I was gonna say this is what a dip switch should. I don't know how well you can see that, but there you go. For people are wondering, that's what a dip switch looks like.
Wait a minute, I can't see it. Let me see. Are you showing it on your camera?
Yes, sir.
Wait a minute. Let me minimize this. Oh, okay. I can't see it. Can you guys see it? Is it switch?
I have to keep talking.
Yeah.
Huh?
Yeah, I could see what Sam was showing.
I can't see it. I'm scared to press the button because I might lose.
Nah, don't worry about it.
No, I want show me at the end though. At the end of the show me. I'm scared if I do something wrong, I'll lose my PowerPoint. I'm not
Sounds
really. But show me at the end. But as long as you guys see it, good. I'm glad you had that. I really should have this stuff for show and tell, but I don't know. They don't give me any money anymore. We had all of this stuff over at the. I don't know if you guys were around when. Do you guys have lab over on Victory Parkway? Do you still have lab over there or not?
Yes, sir.
Yeah.
Okay,
Well,
so
until this happened.
yeah, so before they combined colleges, we were our own separate college of Applied Science, and then the College of Engineering. There were two separate colleges, and boy, we had better labs in engineering. So we actually had a whole POC setup, and I taught the class over there. I taught the theory, and I don't know if you guys know Mark Fassler, but he taught the lab, and we used a simulation software, and then we would go and you actually use an actual POC, and he had all the hardware and the switches. You actually would program and touch this stuff. But I don't know, since they did all this combining and discombobulating and all that, I don't know what's over there anymore. But anyway, well, thank you for showing that switch, the dip switch. I'm going to go through this. These are limit switches. You've seen that in the actual your simulation software. They had limit switches in there. Here is a physical limit switch. Now, they come in all shapes and sizes, but this one has this arm right here has a wheel on it. That's an actual wheel. Sometimes they have a wheel. Sometimes it's just a little metal arm that comes up. And that arm right now is pressed by this cam. That cam moves back and forth on the machine. If I move that to the left, then that arm will move to the left. Inside the enclosure is sealed, so you can't get any. It's sealed, so it stays really clean on the inside of the enclosure. And in there you have either a normally open or normally closed contact that you can connect to. And sometimes you have both. You have three connection points. You have the common, and then you have a normally open and a normally closed that you can connect to. So if you have something that moves back and forth on the machine, like this cam, then you could use something like this. I actually used this in a system. I was fooling around with electric windows on the car. I had a thermal sensor, and what I was trying to do was have the windows lower themselves down when the car reached a certain temperature. And so I built this device, and I actually had this exact limit switch where I put this on the side of the window. It's a small limit switch, and that wheel basically was against the glass, and when the glass lowered and got past the bottom of the wheel, the switch would disengage, and then the motor would let the windows down. But then the problem is I kept current going to the motor when the window was down, because I didn't have the knowledge yet to build a circuit to shut the motor down when the current built up in the motor, which is what happens when you keep a motor energized and it's at the end of its limit. Anyway, a limit switch. This is a really useful device. You'll see these if you have things that move and you need to find position. Limit switches are really, really common. I think I showed you these. I don't know if I showed these or not, but here's some schematic symbols for temperature switches. You can have a temperature switch or a thermostat. You're all familiar with those. If you look at wiring diagrams, you'll see these symbols on PLC or electrical wiring diagrams. Now this next one you'll have to forgive me for. This was my attempt at a pressure switch. I don't know if I told you guys, but back in 2004, I put all this whole course back on PowerPoint because it kept going up on the book price, and I got pissed off. I didn't feel like students have to keep every year the book goes up to the point to where it was like hundreds of dollars. So I put it all on this PowerPoint, and I've been using these PowerPoints. PowerPoints came with a book, but I didn't like their PowerPoints, so I made their own. I made my own set, which is what we're using, and this is my attempt at a pressure switch. I don't know that a pressure switch usually works. I figured if I wanted to design a pressure switch, how would I make it work? I'm sure they would. They have what we call piezo electronic pressure switches. So this is my attempt at a mechanical pressure switch. You guys are METs and mechanicals and all that, so you can design a better pressure switch than I could. But basically, you need to have some kind of device, and usually they use a piezo. If you know what a piezo sensor is, a piezo crystal. It's interesting when you press it, when you apply force on it. I don't know if you call that a strain or stress. I don't know what terminology you guys use, but if I put it between my fingers and if I squeeze this thing real hard, this crystal, it actually creates a voltage. It's interesting, it creates a voltage. If I apply a voltage to it, it vibrates at a very precise frequency, depending on how it's cut and some other factors. It vibrates back and forth. So you can use those piezo, those little sensors. You can use those as a pressure sensor. It's actual solid crystal that if you squeeze it, you get so much voltage. I mean, we're talking probably microvolts, but then you can amplify that. But that voltage is proportional to the amount of pressure on it. So you can use that for a pressure switch. And they actually use those if you have, now I know you guys have digital watches, but the old mechanical watches that were made with crystals actually had these little crystals in it that they would apply a electric current to, and these things would vibrate so precisely they can use those to keep time in a watch. So those crystals would probably be the way that the sensor is done, and I'm sure they have other ways to do pressure sensors if you had to design a sensor. Anyway, here's a symbol for a pressure switch and a schematic. You would see this. Well, I don't know about this. This is this looks like a part of a toilet. But I thought about, all right, if I wanted to make a float, maybe I have a tank. Now again, I'm sure nowadays this is done electronically. Probably have some electronic tape that you run down the inside of a container or a tank, and it would electronically monitor the level of the tank. They can probably do it with lasers. There's a lot of ways to do it. But back in 2004, and I was sitting in my chair figuring out how would I make a level sensor, a level switch. And so I had this float, and I have an arm that moves up and down. The switch is in that housing. That's not too far fetched because if you guys know what a sump pump is, is it called a sump pump? The thing that you have in your basement. Some houses have these
Yeah,
pumps. Yeah,
that's what I call.
is it called a sump pump?
That's what I've always heard them called as.
I think it is called a sump pump, but you'll see something like this where they have a float and an actual mechanical arm that moves up and down with the water level in this little hole or well thing that's in your basement. Now, the problem with any the mechanical devices is, of course, you want to do that electronically if you can because these things wear out over time. It'll wear out. You have to replace it. So any physical mechanical thing you can replace, with an electronic device. It probably has a little bit more life to it. But that's my attempt at a level sensor. And there's these are standard symbols, by the way. You will see these symbols. I made the switches up, but these are the actual symbols that you would see. And then make sure you're aware, you know what a transducer is. A transducer is any device that converts energy from one form to another. And there are input transducers and there are output transducers. I have the definitions on this slide. You can read it for yourself. I have a document, a Word document on Blackboard. I believe it's the one on transducers and sensors. So take a look at that at some point because I may ask questions about it. Like I said, if I do ask questions about it on the exam, you can always just go to since it's a take-home exam, you can go right to the switch. But just be familiar with what a transducer is and realize you can have input transducers and output transducers and know the difference between the two. Yeah, it says see handout. So the handout is on Blackboard for output control devices. That's the one that's missing, but I have it on my Google Drive. So I'll move that over at some point. And that's really it. I don't have anything else in the PowerPoint. This was just a brief introduction to field devices, and there are many, 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 many field devices. We haven't even scratched the surface. But the ones that I talked about are probably the ones that you would see most used in any application of a PLC. But they do have highly specialized devices. So does anybody have any questions over the PowerPoint before I close it?
What slides would you recommend us to look over for the final exam, or just look over everything?
The final exam, what I'm gonna do, is give you a problem where you have to apply, the design 1, 2, and 3 that we did. And if you didn't get a chance to see the design 3, because I only had, I don't think everybody signed in that day, but go back and look at that. I botched up the equation. I got mixed up on my equation. I think you guys helped me get it right. So just try to ignore where I messed it up and go in and just look at the logic of what we're doing. I say that second design problem, the second one, the incinerator, probably give you something similar to that. But that was I think we K-mapped that. I want to give you a 4x4 K-map. So probably a combination of design 2 and 3. It's going to be more like that where you have to do some kind of actual application of taking a word problem, changing it into some kind of Boolean expression, taking the Boolean expression and making it a standard SOP, and then K-mapping and putting that into a truth table, K-mapping it, and coming up with some kind of PLC program that actually works. So it'll be something along those lines. I may have a few things, just kind of peripheral things that I might ask about, something in this slide, but I don't really think I have to give you a slide number because, you'll have it right there. You'll have the test. You can go look over any of the material. The test is not cumulative. I'm not going to ask you stuff back from the first couple of weeks of the semester. I'm going to focus on just program design, the last few things we did this week and last week. I'm going to focus on that. But there may be a few things I didn't get quiz you on or asked about like this PowerPoint that I may pull into it. So I don't think it'll be a thing where you have to write down the slide number because you'll have it right there. You'll have all the material, access to the material right there. So I wouldn't worry too much about that. I'm going to close this if you guys don't have any questions and see if I can get my screen back. Okay. Well, I'm going to miss you guys. This has been a fun course. Can you see me? Can you see my camera?
Oh,
Yeah, now we can see it.
Yes.
Oh, yeah, I don't know. So this is, I couldn't say goodbye because now we're doing this remote stuff, so I'm kind of a little sad. And then, I don't know, it just went kind of fast. In the beginning, things were moving kind of slow, but I think when this virus hit, seemed like we just hit the accelerator to the floor, and man, things went quick. So I don't know. I don't know. I'm going to check in. When did I say I would post the exam? Do you remember? Was it Friday or when? I can't remember what I said.
said Friday and have it due Sunday.
Have it due Sunday? I wanted to because I wanted to be due. I don't want you guys trying to think about my exam and then everybody else's exam. Let's just get it out the way. It won't be that big of a deal. I mean, if you've done the design problems and you followed along and all of that, you'll be fine. So other thing I want to say is just kind of watch Blackboard. I got pretty much all the quizzes graded. I do have some homeworks to put up though. I'll be putting those homeworks up. If there was something you didn't submit, I don't want stuff from week 1 or 2, but if there's some stuff towards the end that you missed, then just send me a text and we'll see how we can work it out. There's some stuff I didn't get a chance to collect before we stopped meeting face to face. then we have to see what we can do about it. If we'll see. We'll just give me a couple more days to finish getting the grades up, and let's just kind of see where everybody stands, and then we'll have another discussion if you need to. What I'll probably do is put a link out there, and just we won't have any more lecture, but I may put this meet to make sure everybody's where they need to be and everybody's okay. We'll just touch base. I may do that on Friday or something like that, and we'll just make sure everybody's all right. So you guys have any questions for me or comments? How come Elijah's the only one that ever opens up his camera? What are you guys afraid of?
My desktop does not have a
I
camera.
don't want you to roast
They're
me
ugly.
again.
Oh, Sam,
Okay.
turn your camera back off.
Yeah, ugly. There you go.
Back off.
All right, I see some smiling faces.
Get it, Sam, turn it back off.
Lord. Who has the dip switch? Can I see the dip switch? Can you show me? Who had the dip switch? Yep, that's the dip switch. Everybody see it? Why do you have that dip switch? Oh, you got, what's that? Oh, that's a, okay, yeah, that's the exact, that switch is the one I have the cam against, the limit switch. So why do you have those? What do you do with those? Are you designing something? Oh, wow, I'm jealous. Okay, all right, so I promised you guys I was going to turn the camera around. Let me see how many people are still on. How many people are still on here? Wow, it's 21 people on here now. I'm scared to do it. When we first started, it was only it was only like 12 people. Now I got 21 people. So I'm gonna turn the camera around so you can see where I'm working. So this is the only time I'm ever gonna do this. This is my actually used to be my bedroom. I had actually put drywall up, and but now it's all ripped up, and so I'm gonna turn this around. I'm even gonna open my basement door. This is embarrassing because this is going on YouTube. I want you to see where I'm working.
You can turn off the recording now.
Yeah, maybe I should do that. Thank you. That way thousands of people. Okay.